Hi guys, today I'm going to talk about principal component analysis. In short form, we say PCA. So this PCA is a unsupervised machine learning technique which is used to reduce the dimension of your data set. So it reduces the dimension of the data set consisting of many variables. No, most of the time in data we have many variables like hundreds and thousands, but all these hundreds and thousands of variables are not important. In that case, we can reduce the dimensions. Reducing the dimension means reducing the number of columns. So we'll build a model with only important features. But here the point to be noted is when you reduce the number of dimensions, you are retaining the variations present in the data sets up to the maximum extent. So this is same as transforming the variables to new set of variables, and we call them as principal components, in the short form PCs. And these principal components are orthogonal. Orthogonal means they are independent, so the correlation between the variables is 0. So here there are some basic terms you need to know, uh, like dimensionality. Dimensionality means the number of random variables present in the data sets, or in other terms we say number of features or number of columns present in the data set. And one more term is correlation. Correlation means how the variables are correlated, how they strongly affect the another variable. So the correlation value is in the range of -1 to 1, and positive correlation indicates that strong correlation. It means if one of the variable increases, then the other one increases. And another type is negative correlation. It means if one variable increases, the another variable decreases. And sometimes there could be no relation. So correlation value is 0. It means there is no dependency among the variables. So whenever we build a model, we expect the strong correlation between the variables, and those variables are included in the analysis. That means when we are separating the data, so we divide the data into x and y. So in x you have to put all the important variables, and as you know, in y we always put a target variable. And one more term is orthogonal. Orthogonal means principal component variables are orthogonal, means uncorrelated. The correlation between any pair of variable is 0. And then what is the meaning of eigenvectors? So eigenvectors or eigenvalues are is a big domain, but when you are doing the analysis, for example, you have a non-zero vector v, and there is a eigenvector of matrix A, and the relation between this v and A is if AV is a scalar matrix of v. In other terms, we write AV is equals to lambda v. So when you multiply A and V, then you'll be getting the output as lambda multiplied by vector. So lambda means here some constant value. So we'll take an example for this. And here, what is the meaning of covariance matrix? So this covariance matrix consists of covariances between the pair of variables. If you consider the item I comma j is the element, then the covariance between ith and jth variable is represented by in the matrix. So let's consider the matrix A as this 2 2 minus 4 8, and then we consider the non-zero vector v as 1 1, and then another vector w as 2 1. So when you perform this operation, AV means multiplying the matrix A with the vector V, then you are getting the result as 4 4 is equals to 4 multiplied by V itself. That means 4 multiplied by 1 1. So that means we have got the output in this format, lambda multiplied by V. In this case, we can say these are the eigenvectors. V is a eigenvector. And let's multiply one more vector, that is A multiplied by W. So we are multiplying the matrix A with the non-vector 2 1, then you are getting the result as 6 0. So we cannot interpret this in this format, lambda multiplied by V, means we cannot get the vector W multiplied with some constant value. So that's why W is not a eigenvector. And these are the advantages of PCA. So the two important advantages of the PCA are when you are training the algorithms, when you are building the algorithms or model, it try to reduce the number of features. So that is the first benefit. And then one more important benefit is it is not always possible to analyze high dimensional data or complex data. So in that case, better reduce the dimensions, use only the important features, and then build a model. So this is the theoretical distribution, discussion, and then when you present your vectors A and W on a two-dimensional space, so here A and V are on the same line. So that means V is an eigenvector here, but not W. So A and W are on different lines. So W is not a eigenvector. So in order to demonstrate this, I would like to I would like to use the famous data set that is a very fundamental data set that is iris. And I hope you guys know what is iris data set, and I have also introduced what is iris data set in my previous videos. So you can refer those videos. So I would like to build a PCA model for iris dataset. So at first I'm importing the important libraries. Import matplotlib.pyplot as PLT. You know matplotlib is used for data visualization to plot various kinds of graphs. And then I have to create a data frame, so that's why I'm importing pandas as PD. And then I'm also importing numpy here. So numpy is used to create multi-dimensional array. So, and also I'm importing Seaborn for very efficient graphs. So as you know, Seaborn is built on top of matplotlib. So the libraries are imported, and then I'm just fetching the data from the open repository that is also known as UCI, which is machine learning repository. So getting the URL, so you can get the data directly from this file iris.data, and then creating a list of feature names. So this data is not having the column names, so that's why we are creating a list of names. So names is equals to sepal length, sepal width, petal length, petal width, and this is our target variable, means type of flower. And then creating a data frame. The data frame name is dataset, so which is user defined, which is equals to pd dot read underscore csv. So we are reading the data from here, and the names are applied, and then displaying the header part of the data. So as you know, head means by default it displays first 5 rows. So these are the first 5 rows. Totally we have 5 columns: sepal length, sepal width, petal length, petal width, and this is the target variable, which is object type. So this is a classification problem. And then checking the shape of the data. Shape means number of rows and number of columns. And if you are aware of the iris data set, so totally we have 150 rows and 5 columns, as we can see over here. And these 150 rows are equally distributed into 50 50 50, means the first 50 samples belongs to the Setosa class, and next 50 belongs to versicolor, and last 50 belongs to Virginica. Then displaying the column names here. So these are the names. So our names, user defined names, are applied. And then at first I would like to build a model without PCA. So I'm just separating the data. X is equals to from dataset dot drop. So we are just dropping the column, and the remaining 4 variables are assigned to X. So this is the name of the column, and then this is axis. Axis is equals to 1, means referring the column, and target variable is assigned to Y. So this is just warning, you can simply ignore it. And then I'm scaling the data, so using standard scaler for data standardization from scikit-learn pre-processing, then creating an object to the standard scaler, and then we are fitting and transforming X, and the result is stored into the X scaled. So data is scaled here. And PCA consists of importantly 2 steps. First is you have to import PCA from scikit-learn decomposition module, and then we are creating an object to the PCA, and here we are not specifying the number of components, so by default it is taking all the components, and then fitting the scale data. So PCA dot fit x scale data, then the model is built. And next I would like to know the variance among the variables. So this is the predefined constant PCA dot explain underscore variance underscore ratio underscore. So this gives the variance. So how much percent the particular variable affect or has a variance. So variance is equals to this one, and then variance is equals to NP dot uh, cumulative sum. So just having a cumulative sum of all the explained variance ratios, and decimal we are reducing to 3, and then multiplying this result by 100, then you can see the variances. That means the contribution of the first variable is 72.8% variance, second is 95.8, means the combination of first two is 95.8, the combination of first three is totally 99.5, and all variables the variance is 100.0. So this is cumulative sum. If you want individually, you can also know. So 70.72 is the variance of first component, and 0.23. So 0.72 plus 0.23, which is equals to 95.8. Then summing first three is equals to 99.5. When all are summed up, then you'll getting 100. So this is the individual variance of each variable. And then importantly here you need to plot a graph which is called as scree plot. So on scree plot you can show the cumulative sum of variables, explain variances of variables. So creating object of figure, then plt dot plot, we are plotting the cumulative sum of explained variance ratio, and this is the title of or label of x-axis, this is label of y-axis, and this is the title of the figure, the train data set explained variance ratio, and then plt dot show. So this graph is showing the component number of components on x-axis and the variance of those components on y-axis. So index starts from 0, so we can consider the contribution, the first variable. The contribution is as we have seen here 72.72%, so which is shown over here. Then 1 means second component, first plus second is 95, approximately 95, and 3 first 3 is 90. How much is that? 95, 99.5. When you sum up all four variables, then the explained variance ratio is 100%. So this plot is called as scree plot. And then I would like to show the variance and have a matrix, covariance matrix. So computed covariance matrix is equals to PCA dot get variance. So this method gives us the variance of the variables, and then we are printing this. So this is exactly printed, and we are displaying the cumulative covariance matrix. So it's a 4 by 4 matrix, and you can see the variance of individual variables. On this, I would like to have a heat map showing the variances of the variables. You can say this is the heat map, and I hope you guys know what is heat map. So if you don't know about this particular graph, you can refer my tutorial on data visualization using matplotlib, and also I have one more video on data visualization using Seaborn, so you can refer to get the basics of data visualization. So you can see the variance among the variables, the first one and the third one 0.88, the first one and the 0 is always 100%, here 1 is always 100%. So these variables, the black colors representing the negative correlation, minus 0.42 in case of third variable, and the second variable. So this shows the variance among the variables. Now As we have seen, the sum of first two variables were 0.72 plus 0.23, which is equals to 95.8. So considering the first two principal components and then building a model. So PCA is equals to principal component of the number of components is equals to 2. So this is a predefined argument n underscore components, and considering the number of components as 2, and then fitting the X scale data to the PCA, then creating a data frame. And to this data frame we are adding the columns like PC1, PC2, principal component 1 and principal component 2, and displaying the header part of the data. So these are the first 5 rows, and we have two columns, PC1 and PC2. Then as we don't have the target variable, so we are doing the concatenation of the data frames df with this data set of class. That means from the original data frame we are adding or accessing class and adding it to the df. Axis 1 means column, then the new data frame is this. So we have principal component 1, principal component 2, and then the target variable class. Next, when you talk about PCA, so you have to you have to have a graph which shows the segregation of data into three classes. So here we are plotting a scatter plot. So how the observations are distributed into three classes: PC1, PC2, segregated into three classes. So first creating object of figure, specifying the figure size, which is 8 comma 6, then having a subplot, one row one column. For the first time, first figure is active, then x-axis label is PC1, and we're also specifying the font size of this label, which is 10. Similarly, y-axis label is PC2, and this is the title of the figure, two PCA components, and font size for that is 15. And we are adding the labels for the target variables. So targets is equals to iris setosa, iris versicolor, and virginica. And as we have three classes, so here I'm going to use three colors RGB, which stands for red, green, blue. So this is a Python list, and then having a for loop for target comma color in zip of targets comma color. So we are getting the target value and then color, and then creating a variable index is equals to df of new of class is equals to target. So target variable and the class target variable here mapping with the data frames class value, and then having a scatter plot of this df new dot location of this index and then PC1 PC2. That means we are projecting the principal component 1 and principal component 2 on our two-dimensional space, and the colors are applied, and then we are also adding legends and then axis dot grid. So this shows the scatter plot, and this is the figure title. So two principal components, and then on x-axis you are having PC1, on x-axis principal component 2, and these are the legends. Setosa represented with red color, and versicolor green color, and virginica is blue color. So you can see principal component 1 is having the classes versicolor and virginica. On y-axis you have a PC2, which is Setosa. Next, I'm going to build a model. So for that, separating the data by using train test split imported from scikit-learn.model selection, and from the new data frame I'm accessing the columns PC1 and PC2, and class is into the variable v, then using the train test split and splitting x and y, which will result as x train, x test, y train, y test, and splitting the data into 80% training and 20% test. And random state we mentioned 0, so we just have the sequence of rows. And then I'm building a first model, that is using the decision tree classifier algorithm imported from scikit-learn.tree, creating object, and then the model always learns from the train data. So fitting x train, y train. So when this line executes, your model is already trained. So once the model is trained, then we can make the prediction for x test. So y predict is a user defined variable, which is equals to our model name is CLF. It means classifier dot predict making the prediction for 20% of X test. Then the results are stored into the Y predict. And then I want to evaluate my model, so importing accuracy score from sklearn metrics, and then I'm formatting the result, so 0.2f, and showing the accuracy here, accuracy score between Y test and Y predict. So Y test means actual value, and Y predict is what the model has predicted for X test. So we can see the accuracy here 90%. So when you are using the only first two principal components, the accuracy over here is 90%. Means 90% it can make correct predictions and 10% it can make mistakes. Next, again building a model. So this time I'm considering all the principal components. So all data X and Y. So again data is separated, and then again splitting data into 80% and 20%. So again scaling the data, applying standard scaler, data is scaled, so scaling both X train and X test, then again applying the PCA. So this time all variables are used, so I didn't specify I didn't specify the parameter n underscore components, so that means all variables are used. And then again building a model, so importing algorithm, creating object, fitting data, and then making the prediction for X test, and then evaluating the model, checking the accuracy score, so which is equals to 80.80. It means when you have built a model with only two principal components, our accuracy was better, so 0.90. When we are using all components, the accuracy is reduced to 80.0. So like this, when you have complex data or when you have high dimensional data, so you can use PCA to reduce the dimensionality of the data set. So first you need to look at the variance, and then always no, the first components are having more variance than the later variables. So this is how PCA is done. So you can also apply apply the same process on any kind of data when you want to reduce the dimensioning after the data. So I have already explained what is the use of PCA. So there are two benefits, right? There are two benefits when you are having complex data. You can apply PCA, and it is not always possible to analyze high dimensional data. In that case, PCA helps us. So that's it from today's session. So feel free to comment, and also do like our videos, do subscribe so that you can get the new videos updated. So thanks for watching.